Welcome to this talk in Automated Vulnerability Checking, Fuzzing Software for Vulnerabilities and Bugs. My name is David Kuczynski and I'm the CEO of AdaLogix. So, who am I? I'm the co-founder of AdaLogix, and in AdaLogix we specialize in doing various research and development projects focused on software security tooling. We also do training in advanced software security topics, especially online training, where we teach students these various topics of program analysis, software security, and automation of these. I have a computer science PhD from Oxford, and in my thesis I specialized in automated analysis of malware. And I've also worked for around 6 years in automated software analysis, both on the defensive and offensive sides of the spectrum. And in general, I have focused a lot on developing pragmatic tools to do solve various software analysis problems. So what's the composition of this talk? We will focus on 4 different points. First, we're going to discuss how has automated vulnerability analysis supported advances in secure development, and this is secure code development. We're also going to talk about what are the technical achievements in the area of automated vulnerability analysis, and also how do techniques transition from academia to industry. Finally, we will have a practical demonstration that shows some of these techniques in practice and how you can use them to find bugs and vulnerabilities. So what is automated security analysis? And here we use security as a synonym for vulnerability analysis. And in order to understand what this is, we first need to understand a little bit of what motivates automated vulnerability analysis. And one of the things that motivates this is that modern software is complex, and some of these software application contains millions of lines of code. So as you see here on the right, this is a small table that shows the lines of code in the Linux version of the Chromium browser. It also shows the lines of code analyzed by a given set of fuzzers. So here you can see the number of lines in the browser, and you can see the total lines of code right here, which corresponds to 5.3 million lines of code in the Linux version of the Chromium browser. And just for reference, 2.4 million of these lines of code has been executed by various fuzzers. That's a very complex program. 5.3 million lines of code has an enormous amount of complexity behind it. And the problem is that this complex code can lead to vulnerabilities, and vulnerabilities in these applications can lead to reliability and security issues, such as program crashes, denial of service, and also execution of attackers' code. And these can have very serious consequences for businesses and people that use these various applications. Automated security analysis is then about developing software tools and techniques to automatically capture software security issues. So automated security analysis is essentially about developing tools and techniques that automatically find these issues in the complex code. So it's about developing programs that analyze other programs. So to go a little bit more into detail about the actual problem that automated vulnerability analysis solves, we can say that essentially the problem is to ensure reliability and security of a given software system. And we can do this, so we can ensure reliability and security of a system in multiple ways, and one of them is, for example, to do manual analysis. However, the problem is that manual analysis is error-prone, so it has pros and cons. It can also be more detailed than automated techniques, but it is also error-prone, and manual analysis is time-consuming, and essentially we don't have enough humans available to go through all of this code that exists by hand. So therefore, automated security analysis also tries to automate what was previously done by manual analysis. And from a very high level point of view, we can go about automated vulnerability analysis in 2 ways. First, we can formally verify that software is bug-free. And this has the benefit that we can actually show that there are no bugs existing. We can prove that a certain piece of software has no bugs. This is, however, a very expensive technique, and it requires a lot of resources. So in practice, it's not really viable to actually, say, analyze a piece of software such as Chromium in this way. The other approach that we can take is to develop tools that analyze the other software with the purpose of finding bugs. And this is cheaper than the verification, and is also what we are going to focus on in this lecture. So in general, when we do automated software analysis, there are two main techniques we can use: dynamic analysis and static analysis. And each of these have quite different properties. So when you find tools within each of these categories, you will find that the tools have pros and cons in quite different areas. So in dynamic analysis, we analyze the code by executing the code and then monitor the state of the application as it executes. So we execute it and then we monitor the state of the application. This technique, the pros of the technique is that it has essentially no false positives. What this means is that when you execute the application and the executing application, for example, fails, then indeed there is a state in which the application fails. So it's very real because it executed. This is a little bit dubious in the sense that you can also do dynamic analysis wrong, in the sense that you can integrate the tooling in a manner it's not supposed to integrate with the application, and then you might actually get, in some sense, false positives, although this is a little bit more technical. The cons of dynamic analysis is that it's quite limited in terms of scalability, in that you need to be able to run the code, which can be tricky. And also it's a little bit limited in terms of scalability of code execution. It's not easy to execute all code in a given program. Although these are cons, they shouldn't be seen as enormously limiting, in that indeed a lot of targets are being analyzed by dynamic analysis, and a lot of the code in each of these targets are also being analyzed by dynamic analysis. But this also has required a fair bit of human effort to integrate this kind of complete coverage of various targets. On the other hand, we have static analysis. So static analysis analyzes the code without executing the code, but rather it focuses on reading the source code of the given program that it's analyzing. The benefits of this is that it's scalable. So we can read the code of any number of targets, and we can read all of the code for a given target. And the con in general is that it has false positives. So because it doesn't execute the target application, it has to do, and static analysis tools often have to do some type of approximation. And with this approximation comes a level of, say, uncertainty. The techniques that we are going to talk about in this lecture, fuzzing, is a dynamic analysis technique. So what are some of the more popular techniques within each of these static and dynamic analysis techniques? So in static analysis, you find a lot of various techniques such as pattern matching, graph-based analysis. Variant-based analysis has become very popular recently, and also a lot of approaches that leverage machine learning-based. So say, for example, where in a machine learning-based technique, you will, for example, have a pattern that encodes some type of vulnerability, and then you use machine learning to identify similar patterns in another piece of code. Dynamic analysis techniques, there are two primary ones, and the first one is, of course, software testing. So software testing has been around for a long, long time, and is perhaps the most used dynamic analysis technique out there. Secondly, fuzzing is the one, and this is the one that we are going to talk about in this lecture, is also a dynamic analysis technique. Now, there are some techniques that are kind of in between, and symbolic execution and its various variations is somewhat in between static and dynamic analysis. It often tries to leverage a little bit from both worlds, especially when you get into techniques like concolic execution. So the main point in symbolic execution is to reason about a program by performing a computation or by performing an execution of the target in a symbolic way. So you treat certain aspects of the memory in a symbolic way, and this can be combined with a concrete execution. So you will, for example, often find a combination of symbolic execution with fuzzing, even though pure symbolic execution is in some sense a static analysis technique, because there's also a level of not executing it, but executing the application in a real manner. So who does actually develop these techniques in terms of automated vulnerability analysis? And we have all of the major technology behemoths out here, such as Google, Facebook, GitHub, Microsoft as well, and they all have a lot of different tools in each of these components, in terms of static and dynamic analysis techniques. So for example, Google has this tool called ClusterFuzz that is used to manage running a lot of fuzzers, and they use ClusterFuzz to run thousands of different fuzzers up in the cloud and essentially fuzz the majority of Google's code base. That's this logo. Facebook, they have this tool called Infer, which is a static analysis tool, and this static analysis tool is originated from academia and then was later acquired by Facebook, and now they have it as an open source tool that is, you can freely download it and use it to analyze your software. GitHub itself, so they have this, they acquired this other company called SEML, which is also a static analysis tool for finding security vulnerabilities, and in particular, it's very it uses this technology called CodeQL that essentially allows you to treat your code as data and then use various queries to search in your code database and do that in sophisticated ways, such that you can specify queries that identify vulnerable patterns in your code. GitLab itself also has a service for offering fuzzing, and they acquired this company called Fuzzit, and they essentially also offer a service that allows users of GitLab to automatically fuzz the software. We also have these dedicated companies. So all of these companies are essentially multi-purpose technology companies, and they're not necessarily pure automated analysis companies. But we have a myriad of these tools as well. For example, we have this Shift Left, Snyk, and DiffBlue that you see here, and DiffBlue, and all of these offer various techniques and tools for automating analysis of software. And I believe all of these are, in fact, static analysis tools, with DiffBlue being kind of a mix, because their static analysis tools is used to automate the creation of testing or unit tests. So therefore, they kind of use static analysis to automate the execution of dynamic analysis. We also have some more earlier startups. So all of these are various startup companies that have started within, I believe, the last 5 years. We also have other pure automated analysis companies. For example, Code Intelligence is a company that focuses a lot on providing fuzzing to various automotive industries and stuff like that. And we also have Fuzzbuzz, we have For All Secure, and we have also another company from the UK called CocoTech. And there's just a lot of players that are essentially offering services in terms of automated vulnerability analysis. And this is just a spectrum. This is just a fraction of the companies that offer these services, and not necessarily, and it certainly is not an exhaustive list of players. And we also have naturally sort of the traditional or companies that have been in this game a little bit longer, such as Coverity and Vericode, and also Fortify. And I believe all three of these companies have been around for more than 10 years. Another company here called Deep Code is also a company that offers static analysis techniques. And it's noteworthy that some of these techniques are very, very very connected to a given technology. So for example, just reading the name of Fuzzbuzz becomes very clear that what they offer is fuzzing, Well, some other companies offer a bit more, both for like dynamic analysis tools and also static analysis tools. I believe both Coverity and Veracode, although I'm not entirely sure about the specific products. But for example, Synopsys offers both static and dynamic analysis tools. I should also say here that I'm not sponsored by any of these companies or any other company to mention their names here. In addition to the players in industry, there is a huge effort also going on in the open source community with a lot of tools to actually that you can clone from GitHub or something similar, and then just start using them with yourself against your code. And we have a lot of different fuzzers. So for example, libfuzzer, AFL, AFL++, WinAFL, HongFuzz, GoFuzz, syscaller, Fuzzly, and more. And all of these tools are available freely online, and you just need to have the expertise in-house in order to actually navigate using those tools. And also quite a few of these tools up here. So I think Infer is open source, and ClusterFuzz is also open source, and ClusterFuzz works very well with libfuzzer and I think also AFL. So those are, you already have there very strong set of tools available by way of open source. There are also some various static analysis tools available online. I believe Yorn is a static analysis tool that is available online, and I think that Yorn is provided by the developers of the Shift Left company, and I think Shift Left also uses some of the technology from Yorn in their core product. There are also other techniques such as Facade is also a tool that's available and built upon the LLVM infrastructure. We also have another tool called Slither, and what's interesting about Slither is that it is a static analysis tool for smart contracts. So we also have program analysis and security analysis tooling available for the smart contract system. And so in that sense, it's a little bit different because all of these are not really meant to be used, and you can probably change them a little bit, or probably major, but they are really targeted more traditional platforms, whereas Slither is targeted various blockchain systems. I believe it's targeted Ethereum. So academia is also a major player in terms of developing these automated analysis tools. And this can also be shown just from the fact that, let's say, various companies over here comes from academia. So for example, Infer, it came from UCL, I think, University College London. And also SEML originated from academic researchers in Oxford, and DiffBlue came from academic researchers in Oxford. I think also the technology behind Shift Left came from academia. And I think Deep Code also originated from ETH Zurich. And I believe Code Intelligence also came, or many of the founders of Code Intelligence also worked a lot in academic program analysis before starting this company. I think also for All Secure, the ideas and concepts developed for this company also originated from academia. Cocotech is also academic. And I think just in general, there's a huge amount of academic development in automated security analysis. And sometimes this transitions into industry as well. But there's obviously a lot more in terms of papers available that discuss various techniques and toolings, and also make open source tooling available for automated security analysis. So I wanted to give some anecdotes of examples of recent impact provided by these techniques in automated security analysis. And there are like three. I picked three examples where the impact is somewhat clear. The first one is the DARPA Cyber Grant Challenge, which was a DARPA-funded tournament around 6-7 years ago, where I think more than $50 million US were invested into this competition. And the goal of this competition was essentially to build an automated hacking system. Various players from both academia and industry participated, and the winner of this competition would then go off with a prize of $2 million US. And so actually one of the companies that I showed in the previous slide, named for All Secure, was the winner of this competition. And this is then the techniques used in this competition has now grown out from the competition and into industry a lot more. And a lot of the techniques that were used in this Cyber Grand Challenge was, amongst other things, symbolic execution, as well as fuzzing. Another example of recent impact is Google's ClusterFuzz and OSSFuzz. So ClusterFuzz is this service that allows you to run a lot of fuzzers in the cloud for many different projects, and OSSFuzz is then an instance, in a sense, of ClusterFuzz that enables you to run fuzzers against open source software. So it's open source software. And this service is provided free. You just, like, the developers of the software just have to integrate the fuzzers themselves, which can take a little bit of effort. And as of June 2020, the OSSFuzz project has found more than 20,000 bugs in more than 300 open source projects. So 20,000 bugs is a quite high amount of number, and a quite high number. And it's also the bugs are very, range from essentially having very little impact to being highly security critical. And they have found bugs in various major libraries, such as, for example, the Go Ethereum implementation and Golang itself. Finally, I want to talk about a third example, which is this lgtm.com, which stands for Look Good to Me. And this is a service provided by the company SEML or GitHub now, which essentially allows you to do much of the same as OSSFuzz does, but with a static analysis tool instead. And that makes them remember that static analysis tool is much more scalable, and they have to date analyzed around 30 million commits, as well as 135,000 open source projects. And although they don't really provide data on the total findings of all this analysis, here's an example of a project that has been analyzed by this SEML product, where you can see that the product found 590 errors and 570 warnings, and also gave 200 different recommendations. So we can see here that there's a significant amount of results from providing these automated vulnerability analysis techniques for open source software. And these are, you can also really feel the impact and magnitude that some of these techniques has had. So how do businesses actually adopt these techniques? Well, first and foremost, there is this huge amount of open source tooling available. For example, we have the dynamic analysis tools such as AFL, AFL++, and libfuzzer, and all of these are used by businesses all over the world as we speak, and they are freely available for download. The only thing you essentially need is to have the right expertise in order to get started with them. There are also static analysis tools available, and these are also being adopted by businesses in order to analyze the software of the given business. And essentially, it's adopted in two ways. Either by getting specialist teams to help integrate the systems. So for example, some type of consultancy or services business that offer services to integrate these various tools and techniques into the software of the given business, and also to train in-house developers in order to be experts in these various tools and techniques, and then have these in-house developers take care of the integration of automated open source automated vulnerability analysis techniques. There's also all off-the-shelf tooling, which is also one of the ways that businesses often adopt these techniques. So there's a lot of players that offer these off-the-shelf tooling where you can essentially buy the product from a vendor. And loads of the vendors I mentioned previously on, I think 2 slides ago, offer this kind of off-the-shelf tooling. But there will often be some level of manual effort still. Okay, so a third option for integrating these kind of automated analysis techniques into your business is to have the services integrated into the development tools that you use. So for example, both GitLab and GitHub offer various services where in your CI/CD pipeline, these various techniques can be run when you sort of like push code up to your projects. And that's also something that's happening, that's being developed a lot, such that the analysis happened instantly when you actually do the coding itself. And I think also Infer is very good at this, in that they provide so like the product itself offers the ability to analyze your code as you are developing the code. So it's not necessarily a thing you run every half a year. You run it almost multiple times a day in some cases. So as I just talked about, one of the big movements that is happening now is to integrate this whole automated security analysis into the software development process much closer than it was previously, and so much more tight into the development process that was previously. And there are these examples of where the code will be analyzed instantly when it's pushed to GitHub or something like that, and that is both offered by GitHub itself and also GitLab, and also Google offers a service for open source projects where you can instantly analyze the code when it is pushed to a given repository. And this is a great way to catch bugs early in the development process. So how do these ideas actually transition from research to industry? So a lot of the ideas, when they are in their early phase in terms of ideas in automated security analysis, come from academia. And essentially a lot of the state-of-the-art tools have academic roots, and we already talked about those. For example, SEML was from the University of Oxford, and DiffBlue as well from Oxford. For All Secure started at Carnegie Mellon University, and Coverity was started by some Stanford academics. And then we also have many efforts in the academic world on fuzzing, and various research labs and also industry companies are now offering, came from an academic background in this domain. So essentially there's a lot of academics that spin out startups from the university world. In addition to this, they can also function as, a lot of academics also function as some type of, provide some type of consultancy for companies developing in-house tooling with the assistance of these specialists. So when you have integrated these analysis systems into your software development process and your whole security arsenal of tools, an important question to ask is, when is enough? And also, how do you pick the right tools? And essentially, there is an enormous spectrum of possibilities in terms of tooling that you can acquire. And it's a good question, when do you know if you have used enough analysis on a given piece of software? And there's no really explicit answer to this. And in reality, I would argue that this depends on the budget, and a more practical question is really how to best spend your budget. So I will talk a little bit more about this in the next slide, but to give an anecdote of how important it can be to continue to analyze your software for a longer period of time, I want to talk about something we did here at Datalogics last year, where we worked a little bit with the Go Ethereum project. So Ethereum is this blockchain infrastructure that is fairly large. And so the anecdote is that Ethereum itself had developed these various fuzzers to analyze their code back in 2018. And it's unclear to me how often they ran these fuzzers against their code, but they did run them routinely and on a more ad hoc basis, I guess. So probably once a week, maybe every twice a week, for a few hours or so. But then in November 2020, Adam from Datalogics integrated this Ethereum into the OSS project, and OSS is a service by Google that would then continuously run the fuzzers of the Ethereum project for hours and days, and just continue to increase the analysis resources put into the Ethereum project. And after a few weeks of analysis, OSS Fuzz then found a 2-year-old bug in Ethereum, and this bug in Ethereum actually was in Golang itself, but it could be used to take down a large part of the Ethereum network, and it had been around for quite a while. So the main point of this anecdote is that the fuzzers that were developed back in 2018 had probably been running for quite a few hours before November 2020, did not find this very security critical DOS bug. But once they were integrated into OSS Fuzz and would then run for, say, weeks, they suddenly found a very important bug that could have fatal consequences for a period of time for the Go Ethereum project. And that's just an anecdote of how important it actually is to do a lot of analysis, so not just stop after a modest amount of time. There are some quantitative measurements that you can use to answer this question of when is enough. And in particular in dynamic analysis, one of the very common metrics for identifying how well you are performing in your analysis is to identify how much of your target code is covered by the tools. So your dynamic analysis will execute the code that you are analyzing, and you can then start to monitor how much of the code, how much code in the project that you're analyzing is actually executed by the dynamic analysis. And over here we can see that the result from Chromium of taking this measurement is actually that, say, 45%, maybe 46% of the code is actually being executed by these given dynamic analysis tools that they're using for this to produce this data. And that gives a very clear indication of what part of the code is being analyzed and what is not. In static analysis, this is not that easy to define, because essentially the static analysis tools will all analyze your entire code base. And the difference is then on their ability to identify flaws. But this relationship between the tools is not perfectly clear. So for example, you can have two static analysis tools that each analyze all of your code. And it's a good question, is it only needed to have just one of these tools, or do you need the two different tools? And is one of them more of a superset of the other tool, and so on? What their relationship is? So the relationship they have in terms of identifying bugs is not very explicit, and most likely they don't themselves have a clear answer. But so if we are looking to have a strong strategy in terms of spending our budget correctly and having a good broad, while also a good broad set of tools in our arsenal, probably the best strategy is to select tools of various characteristics. So you need to have both some static and some dynamic analysis tools, and you should also ensure that you follow the best practices for each of these tools. And also, very importantly, is to have this in-house teams of people that can help use these various tools, and also, more importantly, solve company-specific problems. So even though you have these off-the-shelf often tools that can analyze your code, they can be much more, they can produce much better results if you actually have experts that can use them in a way for optimal output, and that can be done with an in-house team. Finally, depending on your budget, simply increase the above. So if you have more budget, get more in-house experts. If you have more budget, buy more tools, and all this and all this sort of stuff. So fuzzing is a technique that executes a target program with random input over and over again. And fuzzing has found tens of thousands of bugs in recent years, and a lot of the research in fuzzing involves essentially how to create good random inputs. And in this case, good random inputs means inputs that find the bugs. So the way fuzzing detects errors in a program is simply by executing it with the input. And if the program crashes, it means that the input to the program caused it to crash, and thus it means that this input represents an execution of the program that is a bug. So not all bugs actually crash a given system, and some vulnerabilities are silent. What this means is that it's only specific circumstances where a bug will actually crash the system. And to circumvent this, in that to detect these bugs, we use what is called sanitizers. And sanitizers are these kind of bug oracles that can detect silent bugs during runtime. So the research in fuzzing has dramatically increased in recent years. So I did a rough calculation of papers on fuzzing between 2000 and 2005, and it was very few, less than 10 papers or so. And if we compare that to the last 5 years, we have maybe 200 papers in academic conferences of fuzzing. So there's an enormous growth of interest in this fuzzing concept. And the reason for this is that fuzzing is very pragmatic, so it really finds bugs in a very practical manner. So from a high-level perspective, the main research question in fuzzing is essentially how do we increase the probability of finding a bug by generating random inputs. So there's this element of generating random inputs that's at the core of fuzzing. And essentially what researchers want to do is that they want to more efficiently find the inputs that trigger the bugs. And so the first research area that is kind of high level, from a high level perspective, is how can we generate better random inputs. And there's a lot of techniques that will go into looking at the structure of the program, try to infer what kind of attributes a given input should have in order to execute a lot of different code. How can we create various inputs that each trigger different parts of the code, and things like that. And you will find a lot of techniques proposed in this area. For example, symbolic execution is a very important one that tries to calculate various types of input that each will execute a different part of the program. And in this sense, in this research, how do we create better random inputs? Suddenly the random element will often disappear or be removed quite a lot, because often you will start to create a lot of computation and calculations in order to determine good inputs. Another research area is simply how can we faster generate the random inputs. So if we can generate the inputs and execute our code faster, it means that we will have more throughput, and in this sense, more throughput will result in more bugs. Another research area is on how can we create better bug oracles. So this is related to these sanitizers that I talked about in the previous slide, where we want to find silent bugs, bugs that may not actually crash the system. And there's a lot of effort also into how can you actually start to look for logic bugs. So bugs that may not represent memory corruption errors. So memory corruption errors are these bugs that happen in applications written in programs like C and C++, and they're kind of like generic for each application. But logic bugs are bugs that are specific to a given application, and these you can't really generalize in the same manner as you can with memory corruption bugs. So that's another interesting research field in terms of how do we specify bugs better and catch them with our fuzzers. Another research area is how can we automatically instantiate fuzzers. So when you're doing fuzzing, you will often find that you have to write some type of code that will connect your fuzzer with the target application you are analyzing. And this kind of like connection code, the code that bridges the fuzzing engine with your target code, often have to be done by hand. And there's also research in the area of how can you actually automatically connect the techniques and tools of a fuzzing engine to the target code that you're analyzing. It's not just plug and play as of now. There will still be a lot of manual effort in terms of connecting the techniques with your target code. And thus it would be a lot more scalable. It will make fuzzing a lot more scalable if we can simply make it plug and play. Finally, another research area is how to automatically fix vulnerabilities. So some of these fuzzers, as you saw, OSS Fuzz has found more than 20,000 bugs. And essentially the developers have to manually go in and fix those bugs. And this can take a lot of time. So some of these projects that have hundreds of bugs in them, so complex applications, it can be really, really resource heavy to actually analyze each individual bug and make sure you understand the reasons why that bug actually happens. So there's a lot of effort also in terms of, or there's beginning to come effort also in terms of how can you automatically fix the vulnerabilities that you find. And this is also a research area that will have, I believe, much more impact in the following years. So I'm also going to do a practical demonstration, although this will be in a separate video. And I just want to introduce the practical bit here. So we did a fuzzing campaign of a project called FluentBit, and FluentBit is a log processor that handles millions of requests daily. And with this fuzzing effort, we did a lot of manual work in order to integrate the fuzzers with this FluentBit project, which is part of this cloud native computing foundation. We found as a result of the project more than 30 bugs and various security and reliability issues, and this is despite the project had already been audited with manual efforts. So even though that there has been like information security auditors in over the project, there was still quite a fair amount of bugs to be discovered. And this is not to say that auditors are you shouldn't use auditors, because you certainly should, but it's just a way to show that these techniques in some sense complement each other, and you shouldn't leave out, say, fuzzing despite having it thoroughly reviewed by professionals. And in conclusion, this work with FluentBit significantly increased the security posture because we also fixed all of the bugs. So we started to analyze the majority of the code in the project, and suddenly after fixing these bugs, we have a somewhat good guarantee that the code that we analyzed is actually secure for memory corruption vulnerabilities. Okay, so this is the end of my lecture, and I have written down a few conclusions here. So first and foremost, automated vulnerability analysis is on the rise. There's a lot of work going on, a lot of new companies, a lot of academic resources are being put into it, and it's really important to keep an eye out of this if you are running some type of if you're running the security of a company. And my recommendation here is that a strong posture in terms of automated security analysis must focus on 4 different pillars. First, you must have techniques that are both static and dynamic analysis. You must have tools that have quite diverse characteristics in order to get a good broad spectrum. Finally, you should use some commercial off-the-shelf tools as well as open source tooling. It's really important that you also leverage this open source tooling, because there's a lot of energy also put into that. And finally, you should have, given your budget, a set of in-house experts that can really manage all of these techniques, because this is quite a significant effort, and it's not something to look easy upon in terms of we buy a product and then then we have solved the problem. An in-house expert can really do a lot of can push this significantly forward if you have trained them well. So training of in-house experts is also an important pillar in terms of a strong security posture with automated vulnerability analysis. Finally, another conclusion is that you will see security checking being much more integrated into your software development process, and such as the CI/CD pipeline. And this is also something to look out for in terms of you should start integrating these aspects so your code very rapidly is analyzed when it's pushed before it's shipped to production. And there's another benefit of having this kind of instant security analysis when you develop the code, which is that your developers will also become much more security aware, because they will get the security issues presented to them as they are developing, which is neat, because the security attributes will be reinforced as they develop. Some of the challenges that are going to happen is essentially how to, some of the challenges that businesses will have to deal with is finding some type of quantifiable measurement of how secure your code is. This is not very clear, and there needs to be certain improvements in terms of giving a quantifiable status on how good the security posture of a given organization is. There's also training and education of staff in order to manage these techniques properly. That's also a problem that businesses must face. And finally, learning how to use these tools automatically, which is related to training, and then also how to automatically fix these vulnerabilities provided by the tools. So these are the conclusions of my lecture. I hope you enjoyed it, and I hope you will enjoy the practical demonstration that I will give. Thanks for now.